So we did the first few slides in this and looked at some pretty colors on Wednesday. So like the deal is if you have an exchange reaction that can form an insoluble salt, thus the S, right, an insoluble salt, then actually you can write the little solubility equilibrium for that insoluble salt. We could do that for any of those that we looked at on Wednesday. Okay, so so an insoluble salt would ionize, even though it's insoluble, we show it dissolving, right? That's what the stuff on the right is, it dissolving. We can write a KSP expression for it using what we know about writing equilibrium constant expressions like this. So we said that the reaction quotient Q is like a snapshot, right? So Q is at any concentrations. It could be at equilibrium, it could favor the product side, it could favor the reactant side, but that's what Q is, the reaction quotient is. KSP is exactly at equilibrium. One thing as I was kind of looking at the problems that we're going to get to today, do you guys recognize, so this is at equilibrium, right? And so does this make sense? These are saturated concentrations. These are saturated concentrations, okay? So here's the deal then. We can take a snapshot of what the ion concentration is at a given time, and we can plug that into a QSP expression and calculate QSP and compare QSP to KSP, and if they're equal, dang it, you're right at equilibrium, okay? If our snapshot reveals that our reaction quotient is less than our K, okay, we said before, if it's too small, then that means you don't have enough products, because products are on the top. So if it's too small, then you're going to have to form more products. So here in a minute, can you see where actually, if you're talking about a solubility equilibrium, if your KSP is too small, sorry, if your QSP is too small related to your K, then actually more is going to dissolve. So Q less than K or QSP less than KSP, we're going to say more solid will dissolve. If more solid will dissolve, actually, usually when we work these sort of problems, the big thing is there no precipitate. All right. So the other scenario is if you take your snapshot and if your QSP is too big, if it's larger than your K, your KSP, then that means you have too many products. Okay, and we've been talking about if you have too much products, it's going to go back to form the reactants. And in this case, it's going to go back to form the solid. So actually, when we work these problems, does this make sense that at this point, a precipitate will form? That's the crux of it. That's the crux of working this sort of problems. A precipitate will form. Okay, if your QSP is greater than your KSP. Makes sense. It's too big. You have to go back from products to reactants. So I have a slide here that kind of says as much. Okay, so if we look at lead 2 chloride, an insoluble salt, in equilibrium with its ionized form and dissolved in solution. Okay, and if we go ahead and knock out the QSP and compare it to the KSP, by the way, I don't know if this is, I don't know if this is obvious or not, but you guys are good with this. The QSP expression is the same as the KSP. So in this case, it's Pb plus 2 times the molar concentration of the chloride ion squared. Okay? So basically, we can take a snapshot and of what sort of ions we have there. If our QSP is greater than our KSP, then we have too many, see it's too big, so we have too much products. Products are stuff dissolved, so it's going to go back to form the solid. So that's why this says a precipitate will occur. Okay? So I'm bad, like I said, at memorizing things, but I think through things fairly well. So let's work a problem. Oh, by the way, on that last slide, what I want to mention is, and this is already implied, but if the bottom of this, you want to draw a line and say, you know, no precipitate, PPT is my abbreviation for precipitate, no precipitate if QSP is less than K. And that's kind of what we said on the previous slide. You know, no precipitate. All right, so let's do a problem. And there's a lot of kind of bringing in your skills that we talked about before with regard to solution concentration. So I'm into maybe drawing pictures again for these sort of problems because they kind of seem to cry out for it. So here's my beaker. Okay, it says we're going to dissolve 1.20 grams of NaCl, 20 grams NaCl in there. And it said that the solution weighting down here is this. Okay, thanks. Sure didn't, did it? My beaker didn't show up. How's that? Thank you. So that stuff down there is 100.0 milliliters of 0.012 molar PbNO3, so lead 2 nitrate. So you read it a few times, and you're like, all right. One of the things I'm going to right away encourage you, and actually kind of in a way require you, is that you need to be drawing the exchange reaction between the two salts. Two salts here are sodium chloride and lead 2 nitrate. And actually, that's the first thing, item of business I'm going to do here in a minute. So write exchange reaction. The next thing you're going to see on the next slide is I want you to write insoluble equilibria. And actually, you're going to have to kind of use a little bit of we talked about what's going to precipitate out. Well, here they go ahead and they tell you that of the two possible exchange products, so what, we're going to have sodium nitrate, does that look right? And lead 2 chloride, okay? Lead 2 chloride, sodium nitrate. And they go ahead and they tell you that the lead 2 chloride is the thing, okay? PbCl2S blah, blah, blah. And actually, you're going to see the equilibrium on the next page. So those two things. Kind of related to writing the insoluble equilibria, write the KSP expression. KSP expression. And there are other things. So basically, once you have the KSP expression, things look a little bit like, oh, I see. The KSP actually is going to be what? Lead 2 raised to the first power times the chloride ion raised to the second power. So basically, I guess if I was going to write a fourth step there, calculate ion concentrations, and plug into KSP expression. Let's go ahead and do all that. Okay? So those are 4 steps, and you're going to see those 4 steps actually when I kind of give you hints for your homework coming up. So this is the first step. Write the ion exchange reaction. You know, you had the sodium chloride was being added to the lead 2 nitrate. Don't forget to balance it. Okay, so we needed 2 nitrates. Anyway, this is balanced. No, it's not. How do I need to balance it? I sure do. Thank you. Now it's balanced. The second thing I said was to focus on the thing that's insoluble, and go ahead and write the equilibrium for that. Okay, this is balanced. So write the equilibrium for the precipitate that may or may not form. It's a classic general chemistry problem. Will the lead-2 chloride precipitate or not? It's funny, not really funny, but it's almost like, well, you have a 50-50 chance of getting it right? The answer to the question at hand is yes or no. But you guys know you can't just do that. I will laugh and laugh and laugh. Okay. So then, of course, with that, I said don't forget to write the KSP expression. And remember our snapshot, our reaction quotient Q, or in this case QSP, it takes the same form as KSP, or K. Okay, so honestly, do you kind of see where now we can, in fact, I'll write it down there just for kicks. We can calculate a snapshot for this equilibrium by doing this. Okay, and then we're back to what we started with basically today. Compare our Q, our QSP, with our K constant. All right. So the problem is, like the Gen Chem 1 stuff that you learned, you have to get to the molar concentration of each of these. That's kind of the challenging part. So I'll kind of remind you how that looks. All right. So technically, there was no chloride ion in it to begin with, but when we add the sodium chloride, what does the chloride ion concentration become? So here's all the stuff you were given in the problem. In the problem, you said that the mass of the sodium chloride was 1.20 grams. The volume of the solution waiting below it was 100 milliliters. So 1.20 grams NaCl divided by 100 milliliters. We need to get the grams into moles. So we have to, as a side calculation, knock out the molar mass. Molar mass of sodium chloride, 1 mole NaCl per 58.44 grams of NaCl using the periodic table. And then this is technically what we would need to do because we don't want molarity of NaCl, we want molarity of the chloride ion, and they're present in a 1-to-1 relationship. And then last but not least, we need to fix the fact that we have units of milliliters over here. So to get to units from milliliters to liters, we need to introduce that, what we used to use all the time, 1,000 milliliters over 1 liter. And by golly, things that cancel, grams cancel, moles of sodium chloride cancel, left with units of moles of chloride per liter of solution. So it's a wonderful thing, rounding to 3 sig figs. Okay, so the molarity of your chloride ion is 0.205 molar. So that's what we can plug into our our QSP. So do you see right here, we're ready to go ahead and plug in and take our snapshot. So those are the 2 values you're going to see plugged into our QSP. So the lead-2 molar concentration 0.012 was given. The molar concentration of the chloride ion, we just calculated 0.205. Of course, we're going to square that term. It's really easy to forget that square. Rounded to 2 significant figures, our snapshot, our QSP, is 5.1 times 10 to the negative 4th. So Now we compare that, and I've got it down here for us to remember how this works. We compare what we got with our reaction quotient with what our constant is. And if you're like me, I have to concentrate. When we go into negative powers of 10, I'm like, wait a minute, is that bigger or smaller? And when I do it a few times, I see that actually this is larger. Okay, so this is larger, it's too big, so that means we have too much products, and the products are the dissolved stuff. Too much of that, so it's going to have to go back to reactants from products. And what is on our reactant side? It's our solid stuff. So yes, a precipitate will form. That's it. And actually, this one wouldn't be too hard to memorize. If I was going to memorize, I'm like, which way does it go? If Q is larger, if Q is smaller. Well, if it's larger, you're going to get sludge. If it's smaller, you're not going to get sludge. Okay? So that's it. Voila! Precipitate will form. But like I said, somehow I just feel like these should be, I don't know why all my subscripts are missing. These should be SP, SP. Okay. Well then, let's do another one. So here's where I think I said I have some happy news for you. Actually, we are going to skip this part. We're going to skip the second part. And there won't be, and I used to, for years, actually in the last third year to go, don't worry, this won't be on the test. And actually this time I'm going to skip it in lecture even too. But I do want to talk about the first one. So if you were to draw a picture, okay, in this case it looks a little different. We have a beaker and we're going to dump two kind of large sums of liquids in there. We're going to do 200 milliliters of 0.350 molar K2CrO4 potassium chromate, and then we're going to dump a similar amount, 200.0 milliliters of 0.0100 molar AgNO3, okay? And so do you buy this? That actually, once we dump those, our total volume is going to be 400. Does that make sense after we dump them together? So already I hope you're kind of thinking those 3 or 4 steps, I don't know how many steps I had, but you're going to have to write, and I'm going to show you the exchange reaction. So potassium's going to go with the nitrate, and silver's going to go with the chromate. And since we're working in soluble salt problems, you would think something's maybe going to precipitate out. Okay? And I'd have to go back and look at the hints I gave you with regard to solubility. Potassium nitrate is soluble. Silver chromate is the possible thing that's going to precipitate out. So here we go. Let's work this problem. Here's the exchange reaction. Let's make sure it's balanced. This one looks okay. Okay, so the silver ends up with the chromate and the potassium ends up with the nitrate. And so already you see over here, and again, I'd have to, convince myself of this, but I had like 4 or 5 slides early on that talked about general solubility rules, and silver chromate should be in there somewhere as being insoluble. So the next thing we need to do is write the equilibrium of that insoluble salt along with the KSP expression. Okay, so we're going to pick on Ag2CrO4. It is going to break apart into, this is where you're going to have to remember that silver is always a +1 and chromate is a -2. So that's why it combines like that. If you don't remember that, then you're a little bit already kind of maybe not going to get the right answer. So I get 2 of these, in one of those. The KSP expression Of course, that's the same as the QSP expression. So the way we're going to go about this is exactly how we did before. We're going to have to come up with the molar concentrations of silver and chromate that are in that 400 milliliters of solution. And then we're going to plug them in here and come up with a snapshot and compare it to that. That's it. So here we go. We need the molar concentrations of the silver and the chromate. And actually we're going to break it down like this. The moles of chromate added in the 200 mils given that molarity is this. Okay, so the moles of chromate was 0.0700 moles of chromate. Do a similar thing for the moles of silver that came from the silver nitrate. We had 200 milliliters of solution, convert it to liters, use the molarity of the silver nitrate, recognize that you get 1 mole of silver ion for every 1 mole of silver nitrate. Okay, so the moles of silver are 0.00200 moles. And then on the next slide, basically all we need to do is take those moles and divide it by the total volume, which was 400 mils, to get the molarity. Don't you all wish you could go back to Gen Chem 1? You could. So a lot of background stuff to get a yes and no question. Can I just have a yes or no? So here we go. Like you saw on the diagram, as you know, the total volume is 200 milliliters. Sorry, the total volume is 400 milliliters. And since we're adding the around according to decimals. All right, so here we go. The molar concentration of the chromate is 0.175 molar. So that's what we're going to plug in for our QSP. 0.0700 moles divided by 400.0 milliliters times 1,000 milliliters over 1 liter. And then the silver concentration is this. Silver concentration, we take that 0.00200 moles of silver divided by the 400.0 milliliters of solution times 1,000 milliliters over 1. Now we're ready to plug those into the KSP and compare it to, sorry, the QSP and compare it to the K. Here we go. The molar concentration of the silver, 0.00500. Remember, we have to square that times the molar concentration of the chromate, 0.175. Rounded to 3 sig figs. Your QSP is 4.38 times 10 to the negative 6th. Cool. So just to kind of remind you, yeah, if you're like me, I'm like, well, what was the K? I forget. I'll bring the K up here again. Really? Well, I don't have a fancy thing to bring the K up. But what was the K? Can someone remind me? What was the K for? Thank you. Okay, so 1.1 times 10 negative 12. Oh, that's cool. I can clearly see this is larger, so precipitate will form again. You're like, what? Yep, so there's our K, and there's our snapshot. Since that's too large, then we have too much product, so product's going to form reactant, and the reactant is the solid. All right, so that answers that question. So here's where the second part of the problem. So let's see. I actually printed these out. I think I'm going to go get them. I'll go ahead and show this, and you guys can take a gander. And I'm going to go, because it is significant, I'm going to go ahead and part of that question I told you, don't worry about it. It's basically an amount completion. The reason I'm not going to cover those is because I don't include them on my exams, and I just don't want to mess with it. Okay. There is a third problem, and I'm going to just kind of, you saw the title of it, I think, here a minute ago. That problem's entirely out. We still have yet to cover fractional precipitation. The other thing is when I get to an assignment slide, and I will remind you, or you will tell me to remind you, on the assignment slide coming up, the last two problems deal with the percent completeness, so we won't need to do those. Okay, so let's go back to the lecture slides. It'll look like this. Okay, so this one right here, not going to do. It's very doable, but not going to do it. Any of it. So what that brings us up to next is an assignment slide, so we'll take a look at these. Again, right away, if you want to go ahead and cross these off, you could. So let's look at the other ones. Are very similar. That's not it. This looking promising. Okay, so for this one, it basically says you have a solution of two cations. No, this one isn't it either. Dang it. By fractional precipitation. No, it's not time to go home yet. How's this one? This is looking good. Yeah, that looks like what we just did. Okay. So you're going to see me encourage you to do those steps. Those look familiar? Basically, and I think I eventually draw a picture. I don't draw one for a little while. But basically, write the exchange reaction. And I went ahead and kind of got you started. It's not balanced, though. Where you're adding solid magnesium chloride hexahydrate to a solution of potassium fluoride. So magnesium chloride, potassium fluoride, exchange partners. Okay, so be sure to write that. Then go ahead and what's the insoluble salt of interest? They go ahead and say, will precipitation of magnesium fluoride occur? So you can go ahead and break that out, write the equilibrium, write the KSP expression. See, I think doing this will help you, I'm not sure, because then basically you're ready to come up with a QSP, plug these in, and compare it with the KSP that you're going to have to look up. It wasn't given in the problem. So here's finally my diagram. There's this cute little solid magnesium chloride hexahydrate. These waters of hydration don't do anything to the molarity. So you're going to have to use that information to come up with the molarity of the magnesium cation and the fluoride anion. Okay, and then plug those back into the KSP expression. There you go. The next one, then compare that to, you're going to have to look up KSP. Yep, you got it on those little tables. Hope your eyesight is really good. Okay, so for this one, I drew the picture first. Notice that you have a certain volume and molarity of potassium chloride, certain volume and molarity of lead-2 nitrate. Go ahead and write the exchange reaction. Which one will precipitate would be the product, the lead-2 chloride. Write the solubility equilibrium for that and the KSP expression for that. The purple says use your chemistry skills to come up with the lead-2 molar concentration and the chloride ion concentration. Plug them into KSP and compare with, plug them into QSP and compare them with KSP. So again, you're going to have to look that up. This one, again, a beaker. We have solid sodium chloride being added to 1 liter of 0.10 molar silver nitrate. Will the silver chloride precipitate is the question here. And actually there are 3 for this one. Okay, there's an A, B, and C. So this one simply says you're going to have to, from this information, get to the silver ion concentration and the chloride ion concentration, plug them in for the QSP, and compare it to K. B says you're going to put just a smidgen of volume of kind of like 0.05 milliliters of 0.10 molar potassium bromide in 250 milliliters of saturated silver chloride. And they want to know if silver bromide will precipitate. So will this silver connect up with the bromide and precipitate out? So this one is a little bit different in that you're going to have to use, how are you going to get to the silver ion concentration? You're going to actually use the KSP for silver chloride, come to the molar solubility of silver chloride, and that will be the molar concentration of your silver cation. Then you can plug that back into your QSP expression and compare to KSP. Then the last one is up there, C. You're given a small smidgen volume of sodium hydroxide solution, a large volume of, simply it gives you the magnesium ion in terms of milligrams of magnesium per 1 liter of solution. So you're going to have to convert that into molarity. The possible precipitate, of course, would be magnesium hydroxide. Okay, so you work it the same way. And one more. Oh, yeah. So in all problems where you have just that smidgen of volume, that smidgen of liquid, 0.05 milliliters, that volume can be thought not to add volume to your solution. So it makes your life a lot easier. So, for instance, if I pick on that last one, kind of with that hint, if I pick on this one, you know, I have 3 liters here, and I have 0.05 milliliters there. The total volume is going to be 3 milliliters, okay? So don't worry about adding that volume there. And skip or extra credit. I think most of you will skip it. I would. Skip or extra credit. So what I'd like to do, if it's okay with you, is stop there for today and not do fractional precipitation. Good and bad. I kind of wanted you to give you a running start at those sort of problems because there might be one on the test for Thursday. But we definitely will start with fractional precipitation on Monday. And probably on Monday, maybe even start new material. We'll see. Okay, does that work for you guys? Matthew seems disappointed.
I don't think he is.
I can't tell.
I'm disappointed because I have to go to work.
Oh, okay.